Well, thank you very much for inviting me for this, symposium, which actually specifically on a topic which I'm advocating. That's as a next grand challenge, which is to build an AI system to win a Nobel Prize. Okay, I mean, some of you may know I proposed a RoboCup 20 few years ago, which is to build like a robotic system to win the beat the FIFA World Cup champion in the soccer, and the RoboCup grown as a very gigantic organization, and they come up with like a number of scientific results as well as technological results, and many spin-off companies. One of the most successful one is a Kiva System now, which is Amazon Robotics right now, and now, but like RoboCup focusing on the intelligence and the physical capability, which is an agile, dynamic, and a movable environment, and relatively well-defined conditions. Yeah, a Nobel Turing challenge do the completely the opposite. We're talking about like having a deep thinking and an open-ended problem, and you might actually take a time, but you want to solve the major question in the science. Okay, so what we, oops. The goal actually defined is just like RoboCup. By 2050, the AI system that can make a major science discovery that was Nobel Prize in physiology and medicine. I mean, it can be like a chemistry or physics, or probably you don't really have to worry about Nobel Prize, and it can be a technical breakthrough or like a climate change issues as well. But simply I put this physical medicine because the system biology is the area I spent like 20 years, and I see a lot of problems with the system biology or biology in general, and therefore like AI will contribute to the biomedical fields a lot. Of course, it doesn't really exclude in other areas as well. But at the same time, I have like a few papers in Japanese and English, and then a few come. When I first talk about this, like in the first series of talks, like some people say, okay, Dr. Kitano, you might be able to create a machine to discover a lot, but like a Nobel Prize will be given to the persons. It's not for the machines, and then so the goal will not be achieved. But why is this concept interesting? Because I thought I initially come up with this idea as like analogy or like a symbolic. But if you take it seriously about like can AI win a Nobel Prize in reality? That poses like a new dimensions. That's interesting. So like a Nobel Turing challenge is about like to build an AI system which has the highly autonomous decision-making capability and discovery capability to actually discover the major scientific outcome, and a Nobel Committee won't be able to recognize this as AI system or a human being, and then actually give about to the AI machine, and turned out it was actually not the human. So this is really like a Turing test at the highest functional quality of the human capability, and it's actually is a Feigenbaum test. There's a Feigenbaum proposed like with can machine be the equally competent as like a best human in a specific professional field. So like a Nobel Turing challenge is basically this is like a scientist version of the Feigenbaum challenge, which is a variation of the Turing test. Okay. Now, you might actually ask like whether that it's possible to have like a non-human to be able to win Nobel Prize. But actually, it's interesting is like then a mathematician called Nicola Bourbaki actually in reality the people thought this guy exists. But actually, this guy Nicola Bourbaki didn't exist. There was actually 20 young French mathematicians. They come up with the fake name, and then keep writing the papers on textbook. So like and later discovered like this actually is not an individual, and if Nobel Prize Committee will give award eventually to the Bitcoin, a cryptocurrency, if that transform the economy for good, and then it's very clear they have to give an award to Satoshi Nakamoto, because like this is a paper which I show on the screen is the paper which actually defining paper talking about cryptocurrency and the Bitcoin and blockchains. And then, but the problem is we don't know who the Satoshi Nakamoto is. Looks like a Japanese name, definitely it's a Japanese name. But whether it's Japanese individual or a group of people or non-Japanese, like no one have ever met Satoshi Nakamoto. Okay, but like although no one have ever met Satoshi Nakamoto, the idea actually carrying on and is transforming the economy. So if as AI scientists publish like a defining paper, I think the same thing happened like in a Bitcoin. Okay. So by having already defining the challenge as actually making a major discovery and actually win it, what's interesting? There are two sub goals actually. One is that we have to build like an AI robotic system that can perform the biomedical and biotechnology research fully autonomously. At least the major discovery. Okay, this itself is a formidable challenge. But the second thing is whether this AI scientists actually behave like a human work indistinguishable means the machine might be able to make a strategic choice of the topic of the research, what to pursue, and communicating from publication other means to explain the value and the method reasoning behind the discovery and the application and social implication. Right? Otherwise, you won't be able to collaborate with the peers or won't be able to align with the value. That's like an interesting is, machine will be able to make discovery. That's for sure in the future. The question is, what makes a machine discovery more significant or less significant? That's interestingly, that will usually align to the value that the human set. So like a Nobel Prize, for example, given to the machine discovery, which, for example, cure the disease, basically the human disease, right? Or like some discovery which had the social implications. That means like align with the human values. So like a lot of discoveries there. So like what makes one discovery significant over others is actually how that aligns to the value system that we build up. So that means like other machine will be able to make a discovery. It is actually machine will be able to sense actually what is the value system that we are looking into. So this is kind of interesting thing. Okay. And we actually come up with like taking this Nobel Turing challenge as it is, without any compromise, like that with the implication of the challenge. Okay, let me go back to like a reason why I come up with this challenge, and then add one example of the current state of the biomedical research, as many of you already aware. But one of the first biomedical research I did is aging with the Professor Imai in Washington University in St. Louis. And then at that time, like this is like over 20 years ago, and evidence was very sporadic, and then it was like omic stage, pre-omic stage, and then we come up with like trying to get the mechanism of the aging. Okay, but basically, what we want to discover in the at that time, probably still true today, is what is the mechanism behind the specific biomedical phenomena, and what are the molecular involved? What are the interaction in between? So basically, we need to identify molecular mechanism or cellular mechanism and interaction with them, and what are the players, the specific molecule involved. And that combination is something we need to discover as a biomedical discovery. The process can be a specific molecular interaction, molecular mechanism, or it can be a disease, or all the mechanisms can be nested. Okay. At that time, we created like a very simple computer simulations, and it come up with like a specific solution that actually a mathematical model which meets all the experimental evidence at that time, which is a two independent master regulatory genes and an effector gene group, and two processes dominating, and then the mathematical model, then interpretation in what actually the biological mechanism could be. So like with the data, we come up with the mathematical model which will be able to reproduce the various experimental data, and with the mathematical model fixed, and then interpretation of mathematical model is mapping into the molecular mechanism and the interactions. Okay. So we come up with like so basically what is this? What it is possible combination of molecular mechanism and interactions, and there are experimental constraints. All the system constraints, data, and then about the mathematical constraint, and trying to explain that. Okay, actually interesting. We submit the paper, and to the science, and the flat rejected by saying, please identify the genes in the molecule. Okay. And I come up back and say, okay, what are the genes and molecule? And if identify that E4R is possibly the molecule involved in this process, because it's homolog with all basic species and involved in heterochromatin, and identified in E4R. Okay. And it turns out this was actually the longevity-related genes in the yeast, and that became the lead to the sirtuin family. And so this is the beginning of the entire sirtuin story. Okay, and Professor Imai actually go on to the mouse experiment for almost 20 years, and then identify the overexpression of SIRT1, which is the human mammalian homolog of the sirtuin, SIRT2, we're able to increase the longevity, okay, by 10% or 12%. Okay, so like we've been very lucky. in the creating hypothesis computational model and interpreting it to come up with a major discovery. So like this is a process and how long it takes. Like starting from 1994 and human clinical trial going 2016 and it's still going on in the various places. But like if you look at the whole process, hypothesis generation, concept-based hypothesis generation, experimental design, that's basically traditional process. Only place we did exhaustively and with exploring all logical combination of the hypothesis was the computational modeling part. Okay, that part we did very exhaustive. All other part we did the traditional one, which actually is intuitive interpretation based on the best effort of our understanding and try to interpret what a possible interpretation could be, biological reality could be. And we could have been wrong in any of those. We've been simply lucky that we haven't choose the wrong interpretation in the entire process. Okay, but usually it's not that lucky, right? So like in a way, we have omics data and all the high throughput data as well. But like hypothesis generation and thinking about logic behind this, we still actually have to think. And we really have to use our, and that part is not changing at all. And in a way, this is like a scientific discovery at the pre-industrial revolution level. I mean, this is a textile factory in Cambodia, actually, which I traveled like 10 years ago. And it's just like a textile factory like this, and there's a very fast machine on the other side. Still, like all other part, they have to be all the handcrafted. Okay, handcrafted is always nice, but at the same time, it's slow process. Yeah. So the question is, why is the process of scientific discovery? It's a serendipity by accident, scientific intuitions. But what is this? Can we define this computationally? That's a fundamental question. And also, I spent like 20 plus years in systems biology. But the problem with systems biology is that you can do the small, well-defined modern system biology, and and then the computer simulation, do the nonlinear understand, simulations and all that. But the large scale model, it tend to be like a statistical traditional bioinformatics rather than systems understanding. And one of the reasons is it's too complex and data is too gigantic. It's go beyond our comprehension capability. So the system biology is the science for AI. Other than a human alone, or at least like an AI-human hybrid system is much better suited to pursue the system biology. That's my conclusion after pursuing system biology over 20 years. Now, one of the reasons is this cognitive problem exists. Information horizon problem, information gap problem, phenotyping accuracy, you can see all that. And then I don't think I have time to go into all this, but at the same time, for example, that's some of it. Okay, right now, I mean, this is statistics 10 years ago, so it has to be much more. But like annually, 1.5 million paper per year published in the biomedical field alone, and that means 4,000 paper per day. And if you're in oncology or immunology or some like a major field, hundreds of paper published per day, and you won't be able to read it. Although you make a best effort to get all the information, you are doing the research, we're doing the research with only fragmented information available in our head. Okay, so that's what's going on. So like we're just navigating without like a map. Okay, and this is the e-signaling map we created. This is 10 years ago. We did 1,500 papers and manually curated. This is like a 2000 paper or something like that. And then this is the Tourette receptor, and this is all the anti-Alzheimer pathway, all that. So you can build this a few months with a lot of people, but you can't keep going for 10 years and keep updating. It's sociologically impossible because you can't guarantee the career path, and psychologically impossible. People can't really keep doing this forever, right? So like what we need to do, and we actually did, is actually automate the process, because like AI need to be there to support this kind of activity. And it was a labor-intensive process, so we do it in the machine right now. Okay, and now the next one is the minority report problem. We have like thousands of papers talking about for example, one thing, AI activating B, and only few of them talking the other way around. Okay, first of all, can you notice that? Okay, if you notice that, you dismiss as error, or you consider this is a very interesting discovery in a very specific conditions. Okay, so that humans not really good at those things. I mean, can you do that in scale? You can do it probably one specifically, but like in many of the discovery statement biologists make, like you might have exceptions and all that, and we can't really do this in a scale. How can we do that? That's the issue, right? And also, human have a cognitive bias when you actually reason, perceive, and reason, communicate using natural language, and language is highly context dependent. So like it depends on the culture, depends on how you perceive things. One reality you express in some language, and what you appear understand what you're talking about has a slight deviation and keep going. So like there's like a fundamental cognitive bias in the our language system. Okay, so and there are a few more, but like basically it's a limit of human cognitions. For the solutions is, can we use the power of computing, power of AI to solve some of the problem? Okay, some of the good example. This is like a very famous example of deep learning thing. It's like I look at deep learning as original image, and then a show the school bus, and then you identify the school bus. So it's left on the right side. It's a slight noise added, and it's not school bus. Then this deep learning mechanism says it's ostrich, and then difference here is in the middle. And if you look at the very carefully, this looks like a ostrich face, and there's a tons of ostrich face figures like pictures like this in the web, and so it may be actually adapting this error patterns and noise pattern as ostrich. Okay, this is actually originally considered to be the instability of the deep learning, but you might actually take advantage of this hypersensitivity to discover something we haven't seen that. And there's other cases like we can see there are things we cannot see. So like this is for example, like this is like a Huntington disease mouse, and in Huntington, if you have like a CAG repeat is accumulated, you have a behavior anomaly. But we couldn't really found how to do that. And there's a deep learning, visual system, which is a CAG repeat sequencing as a teaching signal, will be able to tell from the behavior what is the level of CAG repeat anomalies. Okay. And this is something we can't really see by ourselves, but the deep learning may be able to tell us. Okay, this is some example how our cognitive system can be assisted by the AI, and we have some applications on biomedical areas and research area, but I'm probably gonna skip this. Okay, now. So so what we are trying to do is trying to create like an engine for scientific discovery. And as Professor Lusking talked about this yesterday, and this is started with the dendro and meta dendro about like visual data by Bruce Buchanan and the Fagenbaum and the team. And then Professor Lusking recently created like, this machine, which he discussed yesterday, about closing a loop to hypothesis generation to experimental design and do the experimental verification of that. And this is one of the landmark achievements. Okay, then how we can move this further. Okay, so in the Professor Lusking one, it was defined, what kind of hypothesis we can generate was relatively well defined in a constrained environment, right? And if you generalize that, and if you go by further, we need to look into the scientific discovery process and redefine it. Okay, so basically, we consider scientific discovery to be a massive search and verification hypothesis space. The question is, how massive we should exploit hypothesis, how fast we can verify that, and how accurately we verify that. Okay, look at a couple examples of Nobel Prize. This one is an IPS discovery, Professor Yamanaka, and then the other one is Professor Shirakawa on the conducting polymer case. Okay, Professor Yamanaka actually found out. Initially, looking at the phantom database, so what are genes involved in a possible cell reprogramming? Found out 24 genes involved, and he put them all, and then they confirmed the cell can be reprogrammed. And then he actually did one out experiment to identify the minimum set, which is now considered as a Yamanaka factor, of the 4 genes which can minimally sufficient to reprogram the cell into the pluripotent state. So this is basically a search and optimization. Okay. That's not easy to do, but of course, like you can redefine as a search optimizations. Shirakawa's case is very interesting. I think it's important. There's an intern come from Korea from his lab, and then who wanted to create the thin film. And then this intern actually screwed up an experiment and then put the material in 1,000 times much more dense than it's supposed to be, and accidentally create the thin film. And then Professor Shirakawa decided to optimize it and establish a method to create like a polyacid thin film. Okay. And then with Alan McDermott and then Higa, he decided to convert it to a very efficient conducting polymer. And then so this is such on the optimizations. The basic basically in accident, this is a very much extended in search space to something unexpected level, and then like optimizations. And then also second round search optimization is make the polymer into the conducting polymer. So the basically two cases, and there are many cases which is very analogous, similar in the search and optimization. Okay, I'm not sure like if all discovery would be like this, probably no, but like, some of the major discovery can be done and redefined as search and optimization. Okay, now given that, a very interesting thing is I'm not claiming all discovery will be made by AI, but I will say it's like AI will make some of the major discovery which will benefit the human. Okay, so the correct distinct claim. Okay, so the what we're trying to do is automate this. I want to do this in a scale. Is first of all we have to do the connections. Okay, we have to be able to use all the lab setup and seamlessly, so that the AI will have like access to that. So like we have to build a connected research lab, and then we have to have like AI assistance for the scientific discovery. That means like it's not autonomous yet, but like and probably it's not entirely automated, but like AI will be able to help science discover. And then probably next AI will be automating process as quite substantial part of us. And then the final part is autonomous process, which is basically identifying what research topic to pursue by the AI themselves. Okay, so like I think that a few steps. So like, we've been building a connectivity platform and an AI platform years. For the Garuda platform is connectivity, and the Gandara platform is the AI framework. Okay. The Garuda platform is the platform. Obviously, if you know the Indian mythology, of course you know Indian mythology, and this is actually bird and Vishnu actually use. Vishnu has been channeling the sea of milk, right? So this is the platform for the drug discovery. Initially, of course, for that, and I got very appropriate name. It's a very general name, but actually has a connectivity among the software and then with the devices. So this is one example of the Japanese government approach to using Garuda, and then combine like a 7 or 8 software together to identify the drug-induced arrhythmia, connected database, and the ADME PK, whole body ADME PK, and a subcellular model, ion channel model, and a whole heart model, and then reproducing all the electrophysiology of the heart for the specific drug-induced conditions under the specific genetic polymorphism. Now we, that's our connection software, but we're talking about Shimazu and other company to combine this with the experimental devices. So the Professor Loskin created a dedicated machine for the specific experimental purpose. What we're trying to do is create a platform combining the off-the-shelf components, like all the devices which is available in the market, available in the research lab, and connects them and try to be able to run a range of experiments which is necessary to make a discovery. Okay. So, and then of course I go to the omics and all that. I'll just skip that. Okay, then the question is how you put the AI. Okay, so this is an example of the work with Professor Kawaoka, a very famous biologist, and then all the avian flu drug discovery. Okay, so what we try to do is like a host targeting drug discovery, and the drug discovery has a specific process. Like one like understanding the mechanism, and then you want to identify a target. And you want to identify the lead compound, and then going to optimize it, and then go to pre-clinical trial. Right? So the first thing we want to do is identify the virus replication cycle. And so this is the replication cycle with the hand-curated initially, but now we do this fully automated, almost fully automated, and then natural language, and then processing using the syntax, also the deep learning as well. And this diagram. White one is hand-curated. This is like a gold standard right now. And then a blue one, green one is like an automated discovery by the machine, which cover like a 75 to 77%, 95 to 97%. And then also like generate the molecular interaction, which is not really curated by the human. And we found out that is actually the one human have not discovered, but they discovered later days where human actually missed out. So like we found out there's a quite substantial knowledge extraction capability. Not only that, we have a machine and the software system, which will be able to create hypotheses, so we're able to predict what will be discovered in the future. So Okay, so we have like the system like that. So like this process became relatively automated right now. And of course, like we want to identify with the given network where we should target. And this is not really the AI, but the control theory and network theory to identify like a given the like a specific biological process, where we're gonna actually inhibit in order to stop that process. So we have like a control theory to be able to do that. And then we use omics data to identify, given the, upper six box is the virus replication cycle or the sub-segment, sub-process. And then box circle in the lower part is the virus-associated proteins. So like virus-associated protein is created and that's interact with the host protein and then, invoke this virus replication cycle, right? So like somewhere in the middle is a protein which we want to target. So the question, the issue is, given this protein layers in the middle, and then control theory analysis will be able to identify what are the effective nodes that we should target. So we now understand where to target it. Okay, then the target prioritization, we do the docking estimation. I just skipped this through because I think I used quite a bit of time, but we did machine learning to be able to identify using a multiple off-the-shelf component, which is not very accurate, but we'll be able to tell, given the target, given the compound, which one to believe. And actually they have the strengths and the weakness. So we'll be able to have the overall or very high accuracy docking simulation. And this is the example. I can actually send you the slide on this, but like it's a highly accurate docking simulation specific domain. In this case, a kinase inhibitor to be able to be good enough level. Okay. Then what we did is exhaust the computational docking simulation, entire pathway, not just target, because there's collateral effects, right? All the protein in the map and then all the compound in the library, we spend like, high performance computing to do this. And then with this computer network effect, and they had prioritize which one is most likely to be the good target and then a good candidate. And then go to clinical trial and then they go to the mouse and the monkey is doing very well. And then of course, like with this kind of method, we can expand further into the herbal medicine. This is the Japanese herbal medicine called the Kampo. We talk like, 4 herbal medicine, which we know to, work very well with the influenza, and then see how it goes. Like because there's a lot of active compound, as you can see in the Ayurveda example as well. There's a lot of active compound. So we got the pipeline, mass spec pipeline to be MCLS and GCMLS, MSMS, and then all that, and identify from the extract, the 352 extract identify among them in the plasma. We only identify the very fraction of them available in the plasma, and some of them which is unknown actually coming in. So like a very interesting dynamics in between. So like about, this. And of course, we found that like if you leave one of the half out from the mixture, and efficacy goes down dramatically. So this is like a combinatory medicine, and then trying to do all the phenotyping effect as well. Okay, so if you want to do this, a number of the active compound which you're talking about is gigantic, and you can do the hand, by hand. You have to do the automated process. You have to do the hypothesis generation experiment by automation if you want to go this. Okay, this is some robot example for the ICE with Japanese government lab, Professor Natsume's place. Like this. Okay, yeah, it's just one example. It can be like a more Tekan kind of robot, well, this kind of robot as well. Okay. So then we also want to build a robotics lab or now fully robotics automated the lab, also like a human robot wet lab as well. This is fun. Okay, why this is important actually? It's very interesting. On the right side, this is a molecular interaction, protein-protein interaction in the human. But this is a mathematical similarity in the mouse and Drosophila deciata against all same mathematical properties. That's very interesting. On the left-hand side, this is actually druggability index. Okay, so K is molecular interaction number. So for example, 50-100, this is a heavy important molecule. And then the likelihood they're going to be drugged if it's very low because it's too important. And when it's druggable, and it's mostly the anti-cancer drug in a traditional one because you stop the cell cycle and you stop the DNA replication, right? But you don't want to touch because that has a major side effect. And the middle layer, this is sweet spot, 5 to 20 is the one actually very good. But at the same time, if you notice that on the lower, the left side, which is molecular interaction 1 or 2 is not very important. It's not really kind of genes and molecule which people don't pay attention, but sometimes very important. It has a reasonable chance that they can actually make interact. But at the same time, each of the molecule has a very low chance of being drug, but it has like a vast, this is the tail side of the distribution. So a lot of them. So like, if you can actually screen them a lot in the number, and you behave at a reasonable yield for the druggability target, druggable compound targeting them. So how can you do that? You can't really assign the postdoc to do that because the chances that you get a drug out of the region is very slow, very low. So you have to do it by like an AI system. Okay. Okay. So in order to do this, we have to be able to do this, in the open platform and open collaboration environment. I think that's very important. I think I'm running up a private time. I think I'll finish in 2-3 minutes. And then I'll have a defined sequence and I have to do the automated process. And then I'll have like a few platform. I got the platform to be able to do the automation. Oops, sorry. This is our text mining system to assist the dynamic interrogation of all the facts and the data. I think that's the range of software tools. And what is the important thing is starting from what we know, we are standing on the shoulder of the giants, so like we can't ignore what has been passed, okay? But the problem is like biomedical literature, we don't know which one is accurate, which one is like error, and which one is even the fabrications. So like we have to start, reason and then infer with the unsound ground, and then I extract the generate hypothesis and verify experiments, and then other data. And this process, we can't really assume this is the what is truth and what is not truth is it's not solid, right? And there are fact the knowledge which is most likely to be true and probably very solid, and which is unlikely to be solid. But like there's some lot of knowledge in the middle. So I'm saying this is a twilight zone reasoning because it's just like a twilight zone because you don't know it's true or not. And one thing you are true, but like overnight it could be disproved, or like found out to be that data was actually the complete fabrications. That can happen in this field. So like this is really kind of chaotic, but we have to create like a filtering mechanism in the circle to be able to clean up that and able to accumulate the knowledge in the solid ground. Of course, knowledge can be completely solid, but so like I have to do like all the scoring as well. The final couple of minutes, I'll talk about like AlphaGo. Okay, we can learn a lot from AlphaGo. That's very interesting. As you probably know, and AlphaGo initial version created by like a large data of the past play and a deep learning able to predict what's next move. And then get a self-play, which is AlphaGo against AlphaGo, and with a Monte Carlo tree search to be able to play the all variety of the play based on the prediction and then some variations. So like by the time AlphaGo play against top humans, AlphaGo experience a vast space of the possible movement of the Go. So this diagram indicates that the outer circle is all possible movement on Go. Okay, it's gigantic, but we define that way. And the red circle is the games in the record, right? This is actually on a fraction of the old movement which has been played in the past. AlphaGo start from there, and then actually use the Monte Carlo tree search and tree, on the self-play, expand its horizon to understand what's going to happen in the vicinity of the, movement which human has played in the past, and then now evaluate it and get the reinforcement learning to be able to play better within that search space, right? And then by the time human play against AlphaGo already knew what will most likely happen in the most of the search space vicinity of the human play. Okay, so that was no wonder AlphaGo is very strong. Okay, but the interesting is AlphaGo 0 was actually more the random search in the beginning. So like this, seed what the human play was discarded as a starting from random, very quickly evaluated became like a better than AlphaGo and the best humans. But what it means the human play in the past, it has been a kind of style of play which human is comfortable, human understand, human will be able to reason for that. But like a game of Go has a space which like a very different kind of strategy and then human haven't explored. Okay, so it's very interesting that we're actually eliminating discard the record as the human bias. Okay, now and then if you apply this to the biology, or like most of the experimental science, we have the AI and machine learning. We need a modern simulation, but we have to have high precision experiment to be able to verify that. So we have like a discovery of the knowledge and a human discovery of knowledge, which is studying there. But like, of course, like interesting is like a machine may be able to discover something human haven't discovered, or human may not be able to understand very easily, but still the scientific, there's no guarantee the scientific truth is in the form that human can easily understand or easily discoverable, but AI may be able to discover that. Now, then how we do this is still, I mean, on the way, but like this, the data and data acquisition, but I mean, the virtual data generation, this is the strength in AlphaGo. But the question is, virtual data generations is fine, but whether that is accurate or not, how can you verify that? In game of Go, that was easy, but in experimental science, how are we gonna do this? And this is really the big challenge, okay? And then, of course, AlphaGo discard the order because of the bias, but like, okay, so there's still like for example, like can you actually strategy can map out the search space, which is likely to be false, but just make sure the fault. Okay, so we need a very different experimental strategies to be able to train the AI and still actually maintain our search space. Okay, and then people might asking that question is very important, which actually they valid right now. But at the same time, the reason why asking that question is very important is because your career is limited and resources limited. Therefore, in order for you successful, you have to ask the right question. Okay, but if an AI to do that, we're not going to eliminate this because there's still the bottleneck of the resource limitation, and you want to answer probably much faster than the lifespan of the machine. Probably you want to make it faster. So like it's not gonna be eliminated, but still like you can ask every question, some of the important questions there. And of course, asking the right question, a relatively short-sighted view, the value system build up. A very important question may be beyond what we imagine would be important, right? So the asking right question, unbiased search of the question could be more important than asking right question. This is the major paradigm shift in the scientific discovery. Okay, so the massive search and verification hypothesis space, this is something we want to do. And if we build this, okay, different question comes in. One universal scientist or like a population characteristic AI scientist. Which one has efficient search space and a verification process. So this is more likely to be this population character AI science. If that is the case, each AI have a distinct character of the path to discovery. Okay, that probably looks like a real scientist maybe because there's a natural order behind it. And if you want to discover this, probably you may likely to discover this. Okay, then it's getting much harder to tell whether the AI system will be like a human or it's a machine. Okay, at the end of the day, we hope to be able to identify what the reality of serendipity by accident intuition, and they define that computationally, define that so we understand much better in the science. So what we're going to happen is not probably mimic the scientific discovery process of human being, but we're most likely to find out alternative form of scientific discovery, which is different from human. We're still able to have to maximize the value by collaborating the human scientists and the AI scientists, and the alternative form of intelligence, and probably accept the science at unprecedented speed, and probably machine will be evolved by itself. We don't know, but that would be very interesting possibility to talk about. Okay, so I'll stop here, and thank you very much. And then I would like to open the floor for the question.
Thank you so much, Dr. Kitano. That was a thought-provoking session. So we will quickly move to the Q&A given the time. So the first question is, what would be your take on AI in disease prediction in humans?
Yeah, I mean, AI and disease prediction. So that means I did. Question is, identify the possible cause of disease and the cure. I mean, this is very active. If that is the question, this is very active area. A lot of pharmaceutical companies now into the AI, and then Japan, Europe, and the US, and then they're very keen to just jump on this, grand challenge as well. And that's a huge issue. And if we can do this, I mean, we can probably rationalize and make it the entire drug discovery much more efficient. So we should be able to spend more effort into the neglected disease as well. I mean, I think speeding up the drug discovery process is very critical.
Absolutely. Yeah. So there are two more questions. Maybe we'll take one and one. You can answer offline if you can stay for a while. This is a quite elaborate one. So does the idea of this Nobel Turing challenge also implicitly imply some kind of an introduction of a general intelligence? The main reason of this question is that any point in time, if the AI discovers something that it was meant to be looking for, then that was its original goal. As mentioned by Dr. Kitano in the sub goals, it should be the machine that makes the choice hypothesis entirely in the first place without the knowledge of other human being. Because if the AI was made to look for something, then the humans that made that AI is arguably more deserving for the prize.
Well, yeah, of course. This is a very interesting question. I think if we to have like a AI to be able to define what to pursue, that requires much broader knowledge than a specific field of the science for sure. If we have to have an AI to automate the scientific discovery, and then target to be defined given by the researcher who actually run the system, and then the AI don't really have to know beyond the scope of the all the scientific area, but the AI have to define what to pursue. They have a much broader knowledge. I'm not sure if that requires like a general AI level, but actually much broader than the specific task-specific AI. So that's very, very interesting question. And then I think that we one step towards like a more general AI. But like a general AI means you want to do our kitchen thing, you want to do the soccer play, and probably AI scientists don't have to be able to play the soccer better than Beckham or those guys, right? So probably not that general, but I think like a much more general than the task-specific AI.
Interesting. So there's one more question. If you can take that offline, just in the interest of time, we can move forward. So
Sure.
thank you so
Yeah,
much.
I'll keep feeding back to the chat box and the QA box.
Yeah, that would be great. And
Yeah.
thank you so much. That was a great conversation, great talk, where how you connected from the plethora of biological information being available to the signal pathways and network pathways that are there for different diseases, and how if it has to be human doing all of this, how much time it could take, and then the role that AI and AI related discoveries can play in there. Thank you so much. That was great. So now moving on, like Dr. Kitano also mentioned about the importance of asking good questions, or the importance of building the mental models. So when AI gets into that phase of doing the scientific discoveries on its own, so that also probably brings in the need of building the right mental models.